In this video, we are going back to our 4-bit adders. This one, the circuit which we made in the previous video. And today we want to make some changes. We want to design a circuit able to operate in two different ways. We want a circuit which can perform an addition between two 4-bit number, A plus B, as this one. But we also want to perform a subtraction. So in this circuit, we want to have two different operations in one circuit. And in order to obtain this, we have a new input pin here. And this input pin, the purpose of this input pin is to control the operating of this circuit. When this input value is 0, the circuit should calculate the addition between A and B. And when this input pin is 1, we want to calculate a subtraction between A minus B. So we want to control this adder with this pin and transform it in adder subtractor. The idea is quite simple. I remember you that when we want to perform a subtraction, we can use the same adder as a normal addition, but we have to make a 2's complement of the second number. So if we want to calculate A minus B, we have firstly to calculate the 2's complement of number B. And we want to make this only when this pin is 1. So when this pin, the value of this pin is 1, this number should be complemented, 2's complement. And I remember you that 2's complement is an operation which is performed in 2 steps. In the first step, we have to invert all bits in our number. And then in the second step, we have to add 1 to the result. So first of all, we have to invert all bits in the number B when this input pin is 1. And to perform this, we need a very simple gate. We already know it. It is an XOR. And I show you here, I put a simple XOR with 2 input, and I name these 2 input in and add sub and an output out. And I show you the truth table of this circuit. And here you can see that when the input add sub is 0, so here and here, the output is equal to the input. So look at this row and this one. When add sub is 0, this is a property of the XOR gate. When one input is 0, the output is equal exactly the same value as the other input. And when this control input is 1, you see that the output is opposite to the other input. So I show you in practice. When this input is 0, I put an input here and the same value is in output. When this is 1, in output I have the opposite of the value that is in the second input. So the idea is to use 4 XOR gate to calculate the opposite of number B. Here is our circuit, and we have 4 XOR gates, and I show you when this input is 0, the output of the XOR gates is equal to the correspondent bit of number B. So B passes unchanged, has no changes when passing through these 4 gates. But when this is 1, you can see that the values in output at the 4 XOR gates is the opposite of the input here. So we have a sort of 4 NOT gates for inverter controlled by this input. When this input is 0, we have no inversion of the number B, and when this input is 1, the number B is inverted. So in this way, we calculate the opposite of B when subtraction is selected. But I remember you that we need 2 steps. It is not enough to make to swap all bits, but we have also to add one. We can do it in a very elegant way, because we can use the carry-in input and connect it directly to this input pin. The idea is when I selected 0, I want to make an addition, and so in this case I have no carry in input and the value of B is not changed, and the circuit calculates a normal addition. You can see this is number 3, this is number 1, 3 plus 1 makes 4. If we want to calculate a subtraction, we put here 1, and so the operation is to first use these 4 gates, 4 XOR gates to invert the B, and second, I use the value 1 as a carry-in, and this adds a 1 to the number. So in this way, using the carry input, I can add a number 1, and this number 1 completes the operation of 2 complement, because at first we have to calculate 1's complement, which is simply switching, swapping the bits of the number, and the second operation is to add 1. So in order to add 1, I simply used this select P. So you can see that our circuit is working properly, because here we have 3 minus 1, which makes 2, and if I select an add operation, I have 2 plus 1, 3 plus 1, which makes 4. And we can also try another operation. For example, I put here the number plus 7, and I try to add the number 7, and pay attention here, because these are 2 positive numbers, and I recognize that they are positive because they begin with 0, but the result is negative because it begins with 1. So in this case we have an overflow. We know that an overflow means that the number of bits of the result is bigger than the number of bits of 2 operands, and in this case pay attention that the number of bits is 3, because the first bit is the bit for the sign, plus or minus. So we cannot calculate this 7 plus 7 because the result is incorrect, because a computer would interpret this number as a negative number. So we have overflow. And you can see that we usually spot overflow, detected overflow, using this carry out from the last adder, and in this case it is impossible to do so because the carry out is 0 in this case, but we have the overflow.